Welcome! In this session, we'll explore an interesting problem from LeetCode, number 1732, find the highest altitude. This problem challenges us to calculate the maximum altitude reached as we traverse a sequence of elevation gains. Together, we'll break it down step by step and discuss an efficient solution. Let's dive in. In this problem, you are a biker riding along a road, and your journey starts at sea level, which is altitude 0. As you travel, you track your altitude changes using an array called gain. Each element in the array, gain, I, represents the net change in altitude between two consecutive points on your route. This change could either be positive, meaning you gained altitude, or negative, meaning you lost altitude. Your goal is to determine the highest altitude you reach at any point during the journey. The input is the gain array representing these changes, and the output is a single integer that gives the maximum altitude achieved. Let's explore some examples to understand how this works. Looking at the first example, the gain array is -5, 1, 5, 0, -7. Starting at altitude 0, we calculate the altitude step by step. At step 0, adding -5 to 0 gives us -5. At step 1, adding 1 to -5 results in -4. Then, adding 5 to -4 at step 2 brings the altitude to 1, which becomes the highest altitude so far. At step 3, adding 0 keeps the altitude at 1, and finally, at step 4, adding -7 lowers the altitude to -6. Among all these steps, the highest altitude we reach during the journey is 1, which is the output. In the second example, the gain array is -4, -3, -2, -1, 4, 3, 2. Starting again at altitude 0, we compute the altitude at each step. Adding -4 at step 0 gives -4, then adding -3 at step 1 results in -7. Continuing, we subtract 2 and 1 at steps 2 and 3, reaching altitudes of -9 and -10, respectively. At step 4, we add 4, which brings the altitude to -6. Adding 3 at step 5 results in -3, and finally, adding 2 at step 6 ends the journey at -1. Throughout this journey, the highest altitude achieved is 0, which occurs at the starting point before any losses. This is the output. In the third example, the gain array is 10, -10, 20, -20. Starting at altitude 0, we first add 10 at step 0, which brings the altitude to 10. At step 1, adding -10 reduces it back to 0. At step 2, we add 20, reaching an altitude of 20, which becomes the highest altitude so far. Finally, at step 3, adding -20 brings the altitude back to 0. Among all these steps, the highest altitude reached is 20, which is the output. Now, let's consider some edge cases to ensure our solution is robust. If the gain array contains only one element, such as gain equals 5, the output is simply 5, as that's the only altitude change. For cases where all the values in gain are negative, like gain equals -1, -2, -3, the biker only loses altitude, so the highest altitude remains 0, which is the starting point. On the other hand, if all the values are positive, such as gain equals 1, 2, 3, the altitude increases at each step, and the output would be the cumulative sum, which is 6. In scenarios with mixed gains and losses, like gain equals 1, -1, 2, -2, 3, the altitude fluctuates up and down, but the highest point is 3. To solve this problem efficiently, you can iterate through the gain array, calculate the current altitude at each step, and track the maximum altitude encountered. This approach runs in O(n) time and uses O(1) space, making it both simple and efficient. To solve the problem of finding the highest altitude, we first consider a straightforward brute force approach. The idea is to start with an initial altitude of 0 and then iterate through the gain array, adding each value to the current altitude step by step. At each step, we check if the current altitude is the highest we've seen so far and keep track of this maximum value. This approach is simple and intuitive because it directly calculates the altitude at each point without needing to store all intermediate results. The key observation here is that each altitude depends solely on the previous altitude and the current gain value, meaning we can efficiently track the maximum altitude as we go. This results in a time complexity of O(n), as we only traverse the array once, and a space complexity of O(1), since we use just a few variables to maintain our calculations. Alternatively, another method involves constructing a cumulative altitude array, where we explicitly store the altitude at each step for additional analysis or debugging purposes. While this approach is functionally similar, it requires additional memory to store the array, making it less efficient in terms of space. In the cumulative altitude approach, we still iterate through the gain array, but this time we build a new array to store the altitude at every step. Once the cumulative array is constructed, we can easily find the maximum altitude by scanning through this array. Even though this method has the same time complexity of O(n) as the brute force solution, it introduces an additional space complexity of O(n) due to the storage of intermediate results. To improve efficiency further, we consider an optimized approach that eliminates the need for extra memory. In this approach, we use a single traversal of the gain array, maintaining only two variables, one for the current altitude and another for the maximum altitude. Both are initialized to 0, and as we iterate through the array, we update these values on the fly. This method not only minimizes memory usage but also avoids unnecessary computations, making it highly efficient. The key insight is that we don't need to store all intermediate altitudes to determine the maximum. We can calculate and compare values in real time during the traversal. The optimized approach stands out as the best strategy for this problem due to its simplicity and efficiency. Compared to the pre-computing method, it is faster and more memory efficient, as it avoids the need for an additional array. While the brute force approach arrives at the same result, the term brute force here refers to solving the problem without leveraging the refined insights that lead to the optimized solution. By focusing on directly calculating the maximum altitude in a single pass with minimal memory, the optimized solution achieves the perfect balance between clarity and performance. However, it's important to note the trade-offs. The pre-computing approach may be useful in scenarios where a complete list of altitudes is needed for further analysis, but the added memory cost makes it less ideal for this problem. Both approaches share a time complexity of O(n), but the optimized method's space complexity of O(1) makes it far superior when the goal is simply to find the maximum altitude efficiently. This combination of speed and minimal resource usage is why the optimized approach is the clear choice. To solve this problem, we start by understanding the journey and how altitude changes are represented. The array gain contains the net change in altitude at each step, and our task is to determine the highest altitude achieved. Initially, the altitude is 0, so we set up two variables, current_altitude, which tracks the altitude as we progress through the journey, and max_altitude, which keeps track of the highest altitude we've encountered so far. Both of these are initialized to 0. Next, we iterate through the gain array. For each step, we update current_altitude by adding the corresponding value from gain. This is because each element in gain represents the altitude change at that specific step, so adding it to the running total gives us the new altitude at that point. After updating the current_altitude for a given step, we compare it to our max_altitude. If the updated current_altitude is greater, we update max_altitude to reflect the new highest altitude encountered. This ensures that, as we traverse the array, we are consistently keeping track of the maximum altitude reached at any point. Once the loop completes, the max_altitude variable will contain the highest altitude achieved during the entire journey, and we return this value as our result. Now, there are a few important insights to note. First, this problem relies on the concept of cumulative sums, where the altitude at any given step is the sum of all previous net changes plus the initial altitude of 0. Additionally, this algorithm is efficient because it requires only a single pass through the array, giving it a time complexity of O(n). It also evaluates the maximum altitude in real time without storing intermediate results, which minimizes memory usage. Lastly, edge cases like an empty gain array are naturally handled, as the initial altitude of 0 remains the maximum in such cases. To implement this algorithm, we use simple scalar variables, current_altitude and max_altitude, which are sufficient for tracking the necessary data. This is because the problem only requires the highest altitude, not all intermediate values. As a result, we don't need any additional data structures, which keeps the solution lightweight. In terms of complexity, the time complexity is O(n), since we traverse the gain array exactly once. The space complexity is O(1), as we use only a constant amount of memory regardless of the input size. This efficiency makes the solution scalable even for large inputs. Let's walk through an example to see how the algorithm works in practice. Suppose the input array is gain equals -5, 1, 8, -3, 2. We start with current_altitude equals 0 and max_altitude equals 0. At step 1, we add gain, 0, which is -5, to current_altitude, giving us -5. The max_altitude remains 0, as -5 is less than 0. At step 2, we add gain, 1, which is 1, to current_altitude, resulting in -4. Again, max_altitude stays at 0. At step 3, we add gain, 2, which is 8, bringing current_altitude to 4. This time, max_altitude is updated to 4, as it's now the highest altitude encountered. Moving to step 4, we add gain, 3, which is -3, reducing current_altitude to 1. The max_altitude remains 4, as 1 is less than 4. Finally, at step 5, we add gain, 4, which is 2, resulting in a current_altitude of 3. The max_altitude remains 4, as it's still the highest altitude. At the end of the example, the final value of max_altitude is 4, which is our result. It's worth considering a few edge cases as well. If the gain array is empty, there are no altitude changes, so the initial altitude of 0 is the maximum. In cases where all elements in gain are negative, the altitude only decreases, meaning the maximum altitude remains the initial value of 0. If gain contains just one element, the maximum altitude is simply the greater value between 0 and that single element. This algorithm is optimized for efficiency, using in-place updates to scalar variables to minimize memory usage, while the single-pass traversal ensures that the time complexity remains linear, even for large arrays. This code solves LeetCode problem number 1732, find the highest altitude, where we are tasked with determining the highest altitude reached during a journey based on an array of altitude changes. The implementation starts by defining the function largest altitude within a solution class. It takes one parameter, gain, which represents an integer list of altitude changes at each step. 1. Initialization, two variables are initialized. Current_altitude is set to 0. It represents the current altitude during the journey, starting at the ground level. Max_altitude is also set to 0. It keeps track of the highest altitude reached so far, which initially is the starting altitude. 2. Iteration, the function iterates through each value in the gain list using a for loop. For each change in altitude, the current_altitude is updated by adding the change to it. This simulates the net altitude after the given step. The max_altitude is updated using the max function to ensure it always holds the highest altitude encountered so far. If the current_altitude exceeds the previous max_altitude, it is updated accordingly. 3. Return result, after processing all the altitude changes, the function returns max_altitude, which represents the highest altitude reached during the journey. ### edge cases. If the gain array is empty, the function will return 0 because no altitude changes occur. If all values in gain are negative, the altitude will decrease with each step, but the highest altitude will still be 0, the starting altitude. If the gain array contains both positive and negative values, the function correctly handles the fluctuating altitude and accurately computes the maximum. This implementation runs in O(n) time, where n is the length of the gain array, as it processes each element exactly once. The space complexity is O(1), since no additional data structures are used. This is the Java implementation for LeetCode problem number 1732, find the highest altitude. The logic mirrors the Python solution, where we iterate through the gain array, updating the current altitude and tracking the maximum altitude reached. Key Java-specific differences include the use of type declarations for variables and the math.max method for comparisons. The code is concise and follows standard Java conventions. In this problem, we are tasked with finding the highest altitude a biker can achieve during their journey, starting at an altitude of 0. The input is an array called gain, where each value represents the net change in altitude at each step. Our goal is to calculate the cumulative altitude at every step, track the maximum altitude reached, and return it as the result. For example, given the input gain equals -5, 1, 5, 0, -7, we start by initializing two variables, current_altitude to represent the cumulative altitude, and max_altitude to track the highest altitude observed so far. Both are initially set to 0. Then, as we process each value in the gain array step by step, we update these variables accordingly. Let's walk through the calculations for this example. First, we begin with the initial values. Current_altitude is 0, and max_altitude is also 0. In the first iteration, the altitude change is -5. Adding this to the current altitude gives -5, and since the maximum of 0 and -5 is 0, the max_altitude remains unchanged. In the second iteration, the change is 1. Adding this to the current altitude of -5 results in -4, and the max_altitude is still 0 because the maximum of 0 and -4 is 0. Next, we encounter a change of 5 in the third iteration. Adding 5 to the current altitude of -4 results in 1, and now the max_altitude updates to 1, as it is the maximum of 0 and 1. For the fourth iteration, the change is 0. Adding this to the current altitude of 1 keeps the altitude at 1, and the max_altitude remains 1. Finally, in the fifth iteration, the change is -7. Adding this to the current altitude of 1 gives -6, and the max_altitude stays at 1 because the maximum of 1 and -6 is 1. After completing all iterations, the highest altitude reached is 1. Now, let's examine a scenario where all the altitude changes are positive. For this example, the input is gain equals 4, 3, 2, 1. We start by initializing current_altitude to 0 and max_altitude to 0. In the first iteration, the altitude change is 4. Adding this to the current altitude of 0 gives 4, and the max_altitude updates to 4 because it is the maximum of 0 and 4. In the second iteration, the change is 3. Adding this to the current altitude of 4 results in 7, and the max_altitude updates to 7, which is the maximum of 4 and 7. Let's continue calculating the remaining iterations. In the third iteration, the altitude change is 2. Adding this to the current altitude of 7 results in 9, and the max_altitude updates to 9 as it is the maximum of 7 and 9. In the fourth and final iteration, the altitude change is 1. Adding this to the current altitude of 9 gives 10, and the max_altitude updates to 10 because it is the maximum of 9 and 10. After processing all the values in the gain array, the highest altitude reached during this journey is 10. This example demonstrates how the algorithm handles strictly increasing gains, where the altitude steadily rises with each step. Next, let's consider an example with mixed gains and 0 values. The input here is gain equals 0, -2, 3, -1, 2. As always, we start by initializing current_altitude to 0 and max_altitude to 0. In the first iteration, the change is 0. Adding this to the current altitude of 0 keeps the altitude at 0, and the max_altitude remains 0 because the maximum of 0 and 0 is 0. In the second iteration, the change is -2. Adding this to the current altitude of 0 results in -2, and the max_altitude is still 0 because the maximum of 0 and -2 is 0. In the third iteration, the change is 3. Adding 3 to the current altitude of -2 results in 1, and the max_altitude updates to 1, which is the maximum of 0 and 1. In the fourth iteration, the change is -1. Adding this to the current altitude of 1 gives 0, and the max_altitude remains 1 because the maximum of 1 and 0 is 1. In the fifth and final iteration, the change is 2. Adding this to the current altitude of 0 results in 2, and the max_altitude updates to 2 because it is the maximum of 1 and 2. The highest altitude reached during this journey is therefore 2. To summarize the key insights from these examples, the algorithm uses two variables, current_altitude, which tracks the cumulative altitude at each step, and max_altitude, which keeps track of the highest altitude encountered so far. At each step, the algorithm updates the current_altitude by adding the current gain value, and the max_altitude is updated to the maximum of its current value and the current_altitude. Since the algorithm processes the gain array in a single pass, its time complexity is O(n), making it efficient even for large inputs. To analyze the time complexity of our solution, we start by breaking it down into distinct steps. First, the initialization of two variables, current_altitude and max_altitude, takes constant time, or O1, since it's a simple assignment operation. Next, we have the iteration through the gain array. Here, the for loop processes each element of the input array, which contains n elements. For every iteration, we perform two operations, updating current_altitude by adding the current value from the gain array, and comparing this updated value with max_altitude to determine the maximum so far. Each of these operations is O1, so the total time spent in the loop is O(n), as it scales linearly with the size of the input array. Finally, returning the result, which is the value stored in max_altitude, is also an O1 operation. Adding these steps together, the overall time complexity of the algorithm is determined by the most significant term, which is O(n). Now, let's examine the space complexity of the solution. First, the input list gain is provided as a parameter to the function, and no additional copies of this array are created, so the memory usage for the input is O1. Next, the algorithm uses two variables, current_altitude and max_altitude, both of which occupy constant space, or O1. Importantly, no additional data structures like arrays or dictionaries are used, meaning there's no extra auxiliary memory needed. Finally, the output of the function is a single integer, which also contributes O1 to the space complexity. Combining all of these considerations, the total space complexity of the solution is O1, making it very efficient in terms of memory usage. When comparing this optimized algorithm to a brute force or naive approach, we can see significant improvements in space efficiency. A naive solution might involve explicitly calculating all intermediate altitudes and storing them in a list or array. For instance, you could compute a prefix sum array representing the altitudes at each step and find the maximum value from this array. While the time complexity of this naive approach remains O(n), as it involves O(n) for calculating the prefix sum and another O(n) for finding the maximum, the space complexity increases to O(n) because of the additional storage required for the prefix sum array. In contrast, the optimized approach avoids this extra storage by maintaining only the current_altitude and max_altitude variables, reducing the space complexity to O1. This optimization ensures that our algorithm is not only time efficient but also memory efficient. Let's consider the best, average, and worst case scenarios for the algorithm. Regardless of the input, the algorithm always processes the entire gain array, so the time complexity is O(n) in all cases. In the best case, even if the array contains only positive or zero values, the loop still iterates over all n elements. Similarly, in the worst case, where all elements are negative, the algorithm still performs the same number of iterations. The average case also involves iterating through the entire array, making the time complexity O(n) across all scenarios. From a mathematical perspective, the for loop executes n iterations, with each iteration performing O(1) operations. This results in a total time complexity of n*O1, which simplifies to O(n). Additionally, the space complexity remains O1 since we use only two variables, regardless of input size. This consistent performance across all cases highlights the efficiency of the algorithm. One common mistake when solving this problem is failing to initialize the altitude correctly. The problem typically specifies that the initial altitude starts at 0, and forgetting this or using the wrong starting value will lead to inaccurate results. It's crucial to double-check the problem statement to ensure your initialization matches the requirements. Another pitfall is misunderstanding the gain array. The gain values represent changes in altitude, not absolute altitudes, so treating them as absolute values will cause your calculations to deviate from the intended logic. Additionally, off-by-one errors and loops are a frequent source of bugs. For example, iterating with an incorrect range, such as range, len, gain, +1, can introduce extra iterations or skip necessary values, resulting in incomplete altitude calculations. Finally, a common oversight is neglecting to track the maximum altitude encountered during the journey. If you only calculate the final altitude without keeping track of the highest altitude along the way, you risk providing the wrong answer if the problem specifically asks for the maximum altitude reached at any point. Another important consideration is writing efficient solutions, especially for large inputs. Using nested loops or performing redundant calculations to compute altitudes can lead to unnecessary increases in time complexity, which will cause performance issues when working with larger arrays. Instead, aim for optimized approaches that minimize computation. From an interview perspective, recognizing patterns like prefix sums can simplify your implementation. Problems involving cumulative changes, such as altitude calculations, often rely on this pattern. It's also essential to handle edge cases effectively. For instance, consider what happens if the gain array is empty, contains all negative values, or has only one element. These situations can easily be overlooked, so always ask clarifying questions during interviews to confirm how such cases should be handled. Furthermore, look for optimization opportunities. For example, solving the problem in a single pass with O(n) time complexity is often preferred over pre-computing additional data structures. Be prepared for follow-up questions as well, such as adapting the solution to find the lowest altitude instead of the highest or handling a stream of data as input instead of a static array. This type of problem is closely related to several others on LeetCode that involve cumulative computations or dynamic tracking. For example, LeetCode 53, Maximum Subarray, uses a similar approach where you find the maximum sum of a subarray, which is conceptually similar to tracking maximum altitude with cumulative sums. Another related problem is LeetCode 121, Best Time to Buy and Sell Stock, where you dynamically track the maximum and minimum values to optimize a result. LeetCode 238, Product of Array Except Self, demonstrates how prefix accumulation can be applied in a different context, calculating products instead of sums. Lastly, LeetCode 325, Maximum Size Subarray Sum equals K, highlights how prefix sums can be generalized to solve for specific targets, reinforcing the versatility of this technique across a wide range of problems. When approaching this problem, there are several methods to consider. The brute force approach involves calculating the altitude at each step using nested loops. While this method is straightforward to implement, it is highly inefficient for larger inputs, with a time complexity of O(n squared). A more efficient option is to use a prefix sum array. By pre-computing the prefix sums of the gain array, you can find the maximum altitude by simply identifying the highest value in the prefix sum array. This approach improves time complexity to O(n), but requires additional space to store the prefix sums. The most efficient method is a single-pass solution using a running sum. Here, you iterate through the gain array once, updating the current altitude and simultaneously tracking the maximum altitude. This approach achieves O(n) time complexity with O(1) space complexity, making it the optimal solution for this problem. Great job! To recap, we solved the problem by calculating the cumulative altitude step by step, which resulted in an efficient O(n) solution. This approach is a great reminder of how simple iterations can solve complex problems. Thanks for watching, and stay tuned for more engaging coding challenges. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!